In a power plant, the condenser and the circulating water system play a vital role in plant operation and efficiency. Together, these components complete the steam-water cycle by condensing the steam that's exhausted from the low-pressure turbine. The resulting condensate then travels through pumps, heaters, and other equipment in the condensate and feedwater system, until eventually the water returns to the boiler, where it's converted back to steam so that the cycle can continue. Part of your job as an operator involves monitoring and controlling the condenser and circulating water system. So you need to have a good understanding of how these components work and what problems can affect them. The basic function of a power plant condenser is to convert steam that's exhausted from the low-pressure turbine into water or condensate. The condensate then passes through the various pieces of equipment in the condensate and feedwater system for processing, and is eventually pumped back to the boiler. In a sense, the condenser serves as a heat sink for the LP turbine exhaust steam and the HP turbine bypass steam. It also serves as a collection point for system drains, such as these headers for a plant's drain manifold. The condensing process improves plant efficiency in several ways. For instance, it allows the purified water in the steam-water cycle to remain within a closed loop so that it can be reused. Specifically, the condensate is pumped from the condenser through the condensate and feedwater system and returned to the boiler, where it is heated to produce steam. The same steam that eventually reaches the condenser again, where it's condensed back to water so that the cycle can continue. Another way the condensing process improves efficiency has to do with the fact that most main condensers operate at a vacuum, that is, at pressure below atmospheric pressure. Since steam enters the turbine at high pressure, the vacuum inside the condenser means there is a significant pressure drop across the turbine stages. And the greater the pressure drop across the turbine, the greater the useful output of the turbine. In addition, the air removal equipment for the condenser, as well as a de-aerator, which is a specialized type of feedwater heater in the condensate and feedwater system, also improve efficiency by removing air and non-condensable gases from the condensate. This air removal process is called de-aeration, and it decreases the amount of oxygen that's dissolved in the water. As a result, the amount of corrosion in the condensate feedwater system and the boiler is reduced. Most power plant condensers are shell and tube heat exchangers. In a shell and tube type condenser, steam flows around the shell side, while cool circulating water flows through the tube side. Here's a simplified illustration of one common type of shell and tube condenser, a single-pass condenser. The condenser shell forms an airtight casing around the entire condensing region. Inside the shell is a tube section, which consists of hundreds of circulating water tubes. Plates called tube supports help align and support the circulating water tubes. Components called tube sheets support the tubes at their ends and separate the steam in the shell from the circulating water in the water boxes on each end of the tubes. During normal operation, circulating water enters the condenser through the circulating water inlet, flows through the inlet water box, and into the circulating water tubes. At the same time, steam enters the condenser through the steam inlet and flows around the circulating water tubes. As the steam makes contact with the cooler tubes, it condenses on the sides of the tubes, and the latent heat in the steam is transferred to the circulating water. Latent heat, as you may know, is energy that when added to or taken away from a substance causes a change in the state of the substance, but not a change in the temperature of the substance. The heated circulating water flows through the outlet water box and out of the condenser through the outlet piping. In this example, the circulating water flows through the condenser only once, which is why it's called a single-pass condenser. If we take a closer look, we can see that as the steam condenses, the condensate drips off of the tubes and flows over devices called de-aeration trays. As the condensate flows over the trays, some of the remaining steam in the condenser flows through it. The steam flow through the condensate helps remove or scrub air and other non-condensable gases from the condensate before it flows into the condenser hot well. The air and non-condensable gases are removed by an air removal system. Another common condenser design is a two-pass condenser. The main difference between a single-pass condenser and a two-pass condenser is on the circulating water side. In a two-pass condenser, a partition divides one of the water boxes into an inlet section and an outlet section. The circulating water that enters the inlet section flows through a set of first-pass tubes, which carry the circulating water into the collection or return water box at the other end of the condenser. From there, the circulating water flows back through a set of second-pass tubes, through the outlet water box, and on through the outlet piping. The steam side of a two-pass condenser is very similar to that of a single-pass condenser. Steam enters the condenser through the steam inlet, condenses on the circulating water tubes, and collects in the hot well. The types of condensers used in power plants are determined by plant design and heat removal requirements. Single-pass and two-pass designs are the most commonly used, but some plants use condensers that have more than two passes. In addition, many main condensers are two-halved designs. For instance, in this two-halved single-pass condenser, the two halves are identical on the tube side of the condenser. The shell side isn't divided. The two-halved design allows half of the condenser to be shut down, while the other half continues to operate. For instance, if there is a severe tube leak or blockage in one half of the condenser, that half can be shut down for repairs while the other half remains in service. That way, the turbine can continue to operate while the condenser is being repaired. Keep in mind, though, that load may have to be reduced during the repair since condenser capacity is less than before. When steam is condensed in a condenser, its volume is reduced tremendously, but air and other gases are not condensed, so their volume doesn't change. If the air and non-condensable gases were allowed to remain in the condenser, they would eventually blanket or insulate the circulating water tubes. This, of course, would interfere with the condensing process. To prevent this from happening, condensers are equipped with an air removal system. The air removal system removes the air and non-condensable gases and helps maintain the vacuum created by the volume reduction of the condensing steam. Another purpose of the air removal system is to establish a normal vacuum in a condenser prior to turbine startup. When a generating unit is shut down, a vacuum breaker is opened to equalize the pressure inside the condenser with atmospheric pressure. Before startup, the vacuum breaker is closed and the sealing water is opened. Then the air removal system establishes a vacuum in the condenser shell. This illustration shows the components that make up a typical air removal system. The system includes suction valves, vacuum pumps, airflow monitors, and piping. Let's look at these components separately. Each suction valve in the air removal system is a manually operated gate valve that's open when a vacuum pump is operating. When the pump is shut down, the suction valve is closed to prevent any backflow through the pump and into the condenser. Airflow monitors or gauges provide an indication of the amount of air being removed from the condenser shell through the outlet piping. If the airflow is higher than normal, there could be an air leak into the condenser shell. Vacuum pumps are designed to remove air from a system and in doing so create a vacuum. The three most common types of vacuum pumps are reciprocating pumps, rotary pumps, and air ejectors. A reciprocating vacuum pump is driven by a motor or some similar device that moves a piston back and forth inside each of the pump cylinders. As this illustration shows, on the inlet stroke, when the piston moves in this direction within the cylinder, it creates a vacuum that's greater than the condenser vacuum. This draws in air from the condenser through the inlet valve and into the cylinder. On the discharge stroke, the piston squeezes the air into a small space, which raises its pressure. The increase in pressure causes the air to flow through the discharge valve and out of the cylinder to the atmosphere. Rotary vacuum pumps are also driven by motors or other driving devices. A common example of a rotary vacuum pump is a liquid ring vacuum pump. Here's an illustration of a typical liquid ring vacuum pump. It has a rotor with a number of blades, an inlet port that's connected to inlet piping, and a discharge port that's connected to discharge piping. The rotor and the ports are positioned off-center in the casing, so that there is more space above the rotor than below it. When the rotor is driven, water inside the pump is pushed outward so that it forms a sealing ring around the rotor. This creates large air spaces near the inlet port and smaller air spaces near the discharge port. The large air spaces create a vacuum near the inlet port that's greater than the condenser vacuum. So air is drawn into the pump, where it's trapped between the rotating blades. The trapped air is forced into the smaller air spaces near the discharge port. As a result, the air's pressure is increased, and the air is pushed out of the discharge port and through the discharge piping to the atmosphere. Air ejectors are commonly called jet pumps because they use high-velocity fluid flow to create a vacuum. As shown in this illustration, a typical steam-operated air ejector consists of a steam inlet and nozzle, an air suction port, and a combining tube. Steam enters the air ejector through the steam inlet and is accelerated through the nozzle. The high-velocity steam flow creates a low-pressure area at the air suction port, which draws in air from the main condenser. The air is pulled through the suction port into the combining tube, where it combines with a jet of steam. This combining process is called entraining. The steam-air mixture flows through the combining tube and then on into an air ejector condenser. There, the steam in the mixture is condensed and the air is vented to the atmosphere. Vacuum pumps and air ejectors can be used in various system configurations to remove air from a condenser. For instance, some plants use a combination of a rotary pump and an air ejector because it allows a large volume of air to be removed from the condenser. Other plants use 2 or more air ejectors connected in series. As shown in this illustration, a 2-stage air ejector arrangement creates a greater vacuum than a single air ejector, resulting in improved condenser efficiency. In this system, steam flow through the first air ejector draws in air from the main condenser. After the air combines with a jet of steam in the air ejector, the steam-air mixture flows into the shell of a condenser, which is often referred to as an intercondenser. There, the steam condenses and drains back to the main condenser, while the air flows into the second-stage air ejector. The steam-air mixture that leaves the second-stage ejector flows into the shell of a second condenser called an after condenser. There, the steam is again condensed and routed to a drain tank or back to the main condenser. The air is vented to the atmosphere. Under normal circumstances, as long as a condenser is operated with properly adjusted controls, it should only require a minimum amount of operator attention. But regardless of operating conditions, you should still monitor condenser performance regularly to make sure that the condenser and the turbine are protected if a problem develops. One variable that operators routinely monitor is the level in the condenser hot well. Improper level conditions in the hot well can adversely affect condenser operation. For instance, a high hot well level could flood the de-aeration trays and the lowest condenser tubes. This condition would reduce condenser efficiency and affect the de-aeration process. On the other hand, a low hot well level could cause the condensate pumps to lose suction, which could damage the pumps or could even cause the pumps to trip. Operators also routinely check the airflow gauges and monitors in the air removal system. Abnormally high readings could indicate an air leak into the condenser. In many plants, operators monitor condenser vacuum by checking manometers that are located in the control room. The manometers indicate whether condenser vacuum is in the proper range for the operating conditions. Circulating water inlet and outlet temperatures are also checked frequently because they can provide information about condenser operation. For example, a high inlet temperature can reduce the amount of condensing that's taking place inside the condenser. It's also important to monitor the difference in the circulating water inlet and outlet temperatures. A higher than normal temperature difference between the inlet and the outlet could indicate reduced flow in the circulating water system or blocked condenser tubes, since either of these conditions can result in less heat being removed from the condenser. A lower than normal temperature difference could indicate scale buildup inside the tubes, which inhibits heat transfer and results in less heat being transferred to the circulating water. Aside from abnormal levels, pressures, and temperatures, another major concern for plant operators is the possibility of condensate contamination. The primary cause of condensate contamination is a circulating water leak into the steam side of the condenser. If such a leak occurs, circulating water, which is impure, will mix with the pure condensate in the shell. Condensate contamination can be detected because the mixing of the two liquids will affect the electrical conductivity of the condensate. This device measures electrical conductivity. If it detects higher than normal conductivity for the condensate, it sends a signal to the control room and a high conductivity alarm sound. The condition is also usually recorded in the trends that are kept by an events recorder. Before a circulating water leak can be located and repaired, load demands on the operating unit and the approximate size of the leak must be determined. If the load can't be reduced, and if the leak is relatively small, the unit may continue to operate while steps are taken to minimize the effects of contamination. Since leaks can cause problems, it is important for operators to report all leaks to supervisory personnel. One important condenser problem that's often hard to diagnose is a drop in condenser vacuum. Low condenser vacuum can be caused by improper circulating water temperature and flow conditions, as well as air leakage into the condenser. If you notice that condenser vacuum has dropped over a period of time, you should check the circulating water inlet and outlet temperatures and circulating water pump discharge pressure. You should also be aware that outside ambient temperature can affect vacuum and power production due to the loss of cooling tower efficiency that commonly occurs during hot summer months. Higher than normal readings for circulating water inlet and outlet temperatures or circulating water pump discharge pressure could indicate blocked circulating water tubes. To remove the blockage, it might be necessary to backwash the tube sheets before conditions worsen. Tube cleaning is a fairly routine operation, but in some cases it may require half of the condenser to be shut down for the cleaning process. If an air leak is suspected as the cause of the low vacuum condition, you should check the airflow monitors or air leak detectors in the air removal system. If the airflow reading is higher than normal, the condenser and every system connected to it must be carefully inspected so that the source of the leak can be found and corrected. Two safeguards that protect condensers and turbines from damage caused by high internal pressure are low vacuum trips and rupture discs. A low vacuum trip is connected to the turbine control system. Several alarms are generally received before a trip. This allows power to be reduced and the required actions to be taken to prevent a trip when the loss of vacuum occurs gradually. In any case, if vacuum drops below a certain set point, the low vacuum trip operates automatically to trip all of the turbine steam valves closed. This stops the flow of steam to the turbine and protects the turbine and the condenser from overpressurization. Rupture discs are protective devices that burst if condenser pressure rises above a specified pressure, allowing a large volume of steam to be vented to the atmosphere. Rupture discs are usually located on the turbine exhaust hood, which is a casing that directs the flow of exhaust steam from the LP turbine to the condenser. In this topic, we looked at the basic function and design of condensers used in power plants, and we examined some common types of air removal systems. We also looked at some routine checks that operators need to perform on a condenser. Now take a moment to try some practice questions on this material. In a circulating water system, cool water is pumped through tubes inside the condenser to absorb latent heat from the exhaust steam and cause the steam to condense. Latent heat, as you may know, is energy that when it's added to or taken away from a substance, causes a change in the state of the substance but doesn't change the temperature of the substance. This simplified illustration shows one type of circulating water system known as a once-through system. In this system, the water supply is typically a large source, such as a river, a lake, or an ocean. Water flows through the system once and then returns to the source. The major parts of the system include screens, pumps, expansion joints, vented water boxes, and piping and valves. There are usually two types of screens used to filter out trash in a once-through system: coarse screens and fine screens. The coarse screens are trash racks, sometimes called trash rakes, are large mesh screens that filter out large debris, such as logs or branches. The fine screens have a smaller mesh to filter out smaller debris. Typically, traveling screens are used for this purpose. They can be rotated in and out of the water as needed so that the debris can be cleaned off. The motor-driven traveling screens cycle based on the differential pressure across them. The circulating water pumps are usually large centrifugal pumps that can pump thousands of gallons of water per minute. Centrifugal pumps have to be filled with water in order to operate. So as illustrated here, a priming system may be used to keep the pumps completely filled with water. A typical priming system consists of a vacuum pump, which removes air from a priming tank to form a vacuum in the piping, and a priming valve, which opens if air enters the circulating water pump for any reason. Expansion joints allow for movement of the piping. In a circulating water system, piping movement may result from the flow of a large volume of water or from temperature fluctuations in the system. In addition to expansion joints, the piping in a circulating water system typically includes a number of valves. For example, many circulating water systems use motor-operated butterfly valves as pump discharge valves. This type of valve is open when the pump is operating, but closed if the pump isn't operating to prevent any backflow through the pump. The same type of butterfly valve is typically used as isolation valves at the inlet and outlet water boxes. During normal operation, these isolation valves are open. However, if one of the water boxes needs to be shut down for maintenance, the isolation valves for that water box are closed so that the water box and tubes can be drained. Some circulating water systems also have connections to a water box priming system and a chemical injection system. The water box priming system removes air from the water boxes. This ensures that the circulating water tubes are always completely filled with water. If the tubes are kept completely filled, maximum heat transfer takes place in the condenser. The chemical injection system adds chemicals to the circulating water to retard the growth of contaminants, such as algae and bacteria. Other chemicals are sometimes added as well to reduce the buildup of hard scale in condenser tubes. If hard scale or other contaminants are allowed to build up, the heat transferability of the tubes will be reduced. Here's another type of once-through circulating water system. In this arrangement, there's a circulating water pump for each water box. A cross-connect or tie valve in the piping can be positioned so that flow through both halves of the condenser can continue even if one of the pumps is shut down. This arrangement allows the turbine to continue to operate even though its load may have to be reduced. Not all power plants are located in an area where there is an adequate water source, such as a lake or a river. For those types of plants and for plants that have to comply with strict environmental regulations, the cooling water is kept within the circulating water system to be recirculated. In order for this type of system to function, a cooling tower is needed. The main function of a cooling tower is to cool the heated circulating water from the main condenser by exposing the water to air. Water that has been cooled by the air flowing through it is stored in a basin located below the cooling tower. The cooled water is then circulated through the system by circulating water pumps. If we look at a simplified illustration of a typical circulating water system that has a cooling tower, we see that with the exception of the cooling tower itself, many of the components in the system are the same as those found in a once-through system. The main difference lies in the fact that the cooling water remains within a closed loop rather than being drawn from a source such as a lake and then returned to that source. In a cooling tower, heat is removed from the water in two ways: by convection and by evaporation. Convection is basically heat transfer to or from a moving fluid. In this case, convection occurs as the cool air flows over the water. The movement of the air causes heat to transfer from the water directly into the cooler air. Evaporation occurs when some of the heated water that's exposed to the cool air changes to vapor. The evaporation of some of the water helps cool the remaining water. There are two types of cooling towers that are generally used by power plants: mechanical draft cooling towers and natural draft cooling towers. Mechanical draft cooling towers use large fans to create airflow through the tower and thus cool the water. Natural draft or hyperbolic cooling towers have a chimney shape and do not use fans. Instead, they rely on the tendency of warm air to rise, sometimes referred to as the chimney effect, to cause the air flow that's needed to cool the water. In a natural draft cooling tower, the warm circulating water is splashed over tray-shaped baffles. This spreads the water over a large surface area. The flow of air through this area cools the water by convection as well as evaporation. During this process, the air is heated and begins to rise. The chimney design accelerates the flow of air up through the tower and thus increases the overall airflow. Atmospheric pressure pushes more air through the tower to maintain the airflow that cools the circulating water. In this topic, we looked at the basic operation of a once-through circulating water system, and we examined a couple of types of cooling towers used in some systems. Now would be a good time to try some practice questions on this material.